We have seen these topics: asymptotic analysis, worst case, average case, and best case. The main idea of asymptotic analysis is for measuring the algorithm efficiency or the time complexity of an algorithm. We have seen that an algorithm don't depend on machine or machine time. Asymptotic notations are mathematical tools for representing time complexities of algorithms. These algorithms can be specified using functions or polynomials, and while comparing algorithms we will be comparing these functions, and these functions can be asymptotically equal or different. They are said to be equal if the polynomials representing those algorithms have the same degree. They are different if they have different degrees. And for performing this asymptotic analysis, we use different notations, and we have seen one among them, that is the big O notation. The big O notation defines an upper bound of an algorithm. That means if we represent the functions gn and fn, if they are the two polynomials referring to two algorithms, then we can write it as big O of g of n is equal to f of n if there exists a positive constant c and another constant n naught, such that f of n is always less than or equal to c into g of n for all values of n greater than or equal to n naught. It will be clear if we look into this graph below. There are two plottings here. One refer to the function fn and the other refer to the function gn, which is multiplied by the constant c. The two polynomials can be evaluated in two different ways. One is mathematical evaluation and the other is asymptotical evaluation. You are familiar with asymptotic evaluation, where we neglect the lower degrees of n and we will be considering only the degree of the polynomial. So when we are relating them with mathematical functions, one will be lower than the other. What we have to do is we have to make the lower function, lower valued function, into a higher one using a constant, appropriate constant. So that constant is used here as c. So originally when we were comparing fn and gn was smaller than fn, and what we have done, we have multiplied gn with c so that it became higher than fn. So it is treated as a bound which is upper to fn, and this will be true for all values of n which is greater than or equal to n naught. It may not be the case for values less than n naught. This method is used only when the two functions fn and gn are asymptotically equal or approximately equal. The second notation is big omega notation. Here again we have two functions, polynomial functions, which are asymptotically equal as we had in big O notation. Here we will be doing the same thing, that is multiplying a function with a constant which is mathematically greater than the other, so that the multiplied function becomes smaller than the other function. Originally, the function was bigger than the other function. So we will be using an appropriate constant for multiplying the higher valued function to make it a lower function. Hence, omega can be considered as an asymptotic lower bound notation. This notation corresponds to the best case, whereas big omega corresponds to worst case. Generally, best case performance of an algorithm is not useful, or we will not be considering best case. Hence, omega notation is the least used notation among the three major notations. So the first one was big O notation. The second one is big omega notation. Big O notation corresponds to the worst case of an algorithm, and big omega notation corresponds to the best case of an algorithm. The definition of big omega goes like this. If big omega of g of n is equal to f of n, then there exist positive constants c and n naught such that c into g of n is always less than or equal to f of n for all values of n which is greater than or equal to n naught. The definition will be clear when we look into the graph or plotting below. So these are the two functions. One is fn, other is the gn. So originally gn was greater than fn when we made the mathematical calculation. Our assumption is like that. Then we use a constant c to multiply the higher function gn, so that it can be made as a lower bound to fn for all n which is greater than or equal to n naught. So that is omega of gn equal to fn. The only difference between these two, that is big omega and big O notation, are the greater than less than equality among fn and gn. We will be using a constant to make one function either smaller or bigger for some values of n. The next one is the theta notation. There may be cases where there is no best case or worst case. In such situation, we will use theta complexity. We have seen earlier that for worst case we will be using big O notation. For best case we will be using big omega notation. Otherwise we will be using theta notation. For example, if we want to find sum of some natural numbers, n natural numbers, then there is no best case, there is no worst case. Whatever numbers we have, we will be adding them. In such cases, we will be using theta notation. The theta notation bounds a function from above and below. So let us see an example or this graph. Theta of gn equal to fn such that there exist positive constants c1 and c2 and n naught such that c1 into gn and C2 into Gn will be the upper and lower bounds to Fn. And this is true for all values of n greater than or equal to n0. So this will be the Fn function. We are having another function Gn, and we will be using two constants C1 and C2. When we multiply the function Gn with C1, that plotting will be lower bound, and when we multiply Gn with C2, it performs the upper bound to Fn. That is theta, big theta notation. For example, if the time complexity of n is equal to theta of n square, time complexity of a function is equal to theta of n square, then we can have Tn, that function, as n square plus n plus 5. Why? Because the degree of this polynomial is n square, which is equal to this term. So the theta complexity is equal to the degree of this polynomial. So this is allowed. If Tn is equal to n plus 10, then the degree of this polynomial is 1, whereas this is 2. This is n square and this is n, which is not allowed. Why? Because this function is of lower degree. For theta representation, we should have equal degree of these functions. Then the other example is, if Tn is equal to n cubed plus n square plus n, then the degree of this function is n cubed, whereas degree of theta is n square. This being higher degree, we cannot allow this to be a part of this equation, because T of n will not match with theta of n square. So in summary, we can say that big O notation will have this equation, T of n equal to big O of Fn. We can interchange this Fn and Tn. Tn can be replaced with Xn or Hn or Gn likewise. So order of growth of Fn will always be greater than or equal to T of n in big O notation. When we come to big omega notation, again the equation will be T of n equal to big omega of f of n. Here also we can interchange these two if they have the same degree. Then order of growth of Fn will always be less than or equal to Tn. For big O, it will be greater than or equal to Tn. For big omega, it will be less than or equal to Tn. In the case of big theta, the order of growth should be equal. Fn should be equal to Tn. Asymptotically, Tn and Fn should be of equal degree. Now these are asymptotical relations.